Okay. So where we were last time was that we discussed the law of total probability, right? Which basically allows us to consider, right, cases when we compute a probability. Okay. And so you should look at these EIs, right, E1 to EN, as cases, right, that are extra to the event that you're calculating. For example, right, F here is the event that you will bring an umbrella, right? And the EIs are the state of the weather, right? The requirement is that they have nothing in common, right? And their union, right, is the whole sample space. So it's called a partition. And if we have that, then using, this is just, right, by definition of the axioma probability, and then using the multiplication rule, right, then we will have this so-called, right, the law of total probability. Again, right, it allows us to basically break a calculation, right, of an event, probability of an event down to just cases. There is also a conditional version, right, of the above. And here we only present it in, right, the case of G, right, and G complement, right? So basically, you have a conditional probability, right, of E given F that you want to calculate. And then, right, you want to include the two extra information, right, of case G happens or not. And then you pay it back by multiplying with, right, the conditional probability of G and G complement given F. And so, right, the example for that, right, is exactly this one right here, right, where, so basically, right, when you have a scenario here where you have a team, right, given a team that leads 3-0, right, you want to find a probability that that team wins the series. And here, right, the ambiguity or the extra case, right, the extra information we want or we need is which team, right, that we want to continue, right, to win the series. Of course, right here, the question makes sense that way, but the calculation just simply cannot be done, right, in that ambiguity. So we want to throw in the extra information by, right, conditioning on the extra part where A leads and then multiply back, right, with the conditional of A leads given one team leads, and then, right, B leads, and then, right, so forth, right? So that's the application, right, of the law of total probability, but conditional version. And so beyond that, right, then we continue, right, with you could look at this as an application of the law of total probability, but not quite, right? Bayes' formula stands on its own. They're all connected, right? Basically manipulating the conditional probability for achieving, right, different purposes. Here, Bayes' formula at the heart of it, right, seems like to basically switch the order of conditioning, right? You have F given E, and then you want to kind of reverse the conditioning to E given F, right? Of course, it's not just F given E, right, that you need F given E and F given E complement to reverse the order, right, of conditioning. But the point, right, is that basically you sometimes want to traverse the tree backward, right? So you have E here and E complement, and then for each branch you have F and F complement, right? Like that, right? So you have F given E and F given E complement, right? And notice that the nature of the tree representation here, right? Like this. So for example, when you do, let's say 0.2 and then 0.3 here, right? This 0.3 here, right? Notice is not P of F, right? this 0.3 here is not P of F, at least in the meaning of the tree representation, right? We write 0.3 there, but that 0.3 is the weight starting right at E. Because for example, you could have started here with 0.5, right? So really, right, that 0.3 there is P of F given E, right? And that 0.5 there is P of F given E complement, right? So the tree representation, because you move from node to node, it has that kind of meaning, right, in this representation. And so normally or naturally, for some reason, right, you traverse the tree forward, right? Again, right, the easiest thing to think of is like basically COVID, right? Not COVID, right? And then test positive, right? Things like that, okay? But so that's kind of the not the natural, but how the state of things are. But when you look at the information, you tend to traverse information from the back, right, to the front, meaning that, right, you want to know if you test positive, what's the chance of you having COVID, or for that reason, if you test positive, right, what's the chance of you not having COVID, things like that, because right, it could be a false positive case. So Bayes' formula is really conducive, right, or exactly is tailored for this kind of purpose, right? And that's sort of like the meaning of like switching conditioning here, okay? And but from some point of view, right, from the flow of discussion, you can see that it's actually a natural continuation of, right, the law of total probability, okay? But of course, from that point of view, right, you can also have a traversing backward, right, on the tree for more than one case, right? For example, here, instead of just branching to E complement, you could have, E1, E2, E3, E4, right? I don't know, right? And then each of them have an F and F complement, right? So I don't know, right? Maybe some kind of disease, right? And then there's a test for it, but there are four possible variations of it. I'm not sure, right? I mean, can cook up an example that sounds very convincing on the spot, but something along that line, right? So anyway, right, then you can also want to traverse backward to see, right, that, oh, you know what? Yeah, right, once you're here, right, yeah, exactly, right? When you want to traverse backward and see, say, what's the probability you are exactly on the second branch, for example, right, if you come out as F, okay? Anyway, so that's that. And so we did look at, right, this example, which is a very easy example of, right, kind of, right, Bayes' formula traversing the tree backward, right? And then we move to here. So this one, right, has a conditioning flavor, as you will see, but it's actually also a challenging problem in terms of interpreting the structure, right, of the game itself or the problem itself, right? So here, the key, right, to analyzing this game is again that basically, right, you have two players that play until one has two more points than the other, all right? And so when you look at that, right, you will see that, first of all, right, this game cannot be played for an odd amount of time. The reason is, right, either for each of the round of two games like this, right, either they tie and then they move on to the next round, if you will, or, right, one of them will win that round and then the game would end. So either way, right, a game cannot end mid-round like that, right? Because if you end mid-round like that, you only have a 1 point lead and you can't have a 2 point lead, okay? So basically, right, that analysis, which is not really sort of spelled out in the problem for you, but you have to think about it, sort of controls or helps us, right, to understand the structure of this game, okay? So having said that, I guess let's just start with that question, right? What's the probability that this game will be played 2n times? 2 times n, right? 2n times, or right, the number of points is 2n. What would the answer be? Any suggestion? So the game, right? If it so basically notice the structure of the game is such that, right? If you look at this as 2n, for example, and what happens is the last round must be the determining round, right? Meaning that it must end when one of the player wins. So, right, like that, right? And then all the previous rounds, right, must be draw. So basically, right, that's draw. And then you have 2n minus 2 over 2. And then that's A win, and that's B win. Okay. Any question?
Wait, I'm sorry. Can you go over that formula again that you just wrote down?
Yeah. So if you look at, right, any game, right, with any length, right, then it ends at that length because the last round must end at AA or BB. Okay, that's the winning round. So the probability of that is determined here, right? AA or BB. All the previous rounds must be drawn. Draw. The probabilities of draw is as follows, right? The 2 is because of the permutation. How many rounds are there previously? Well, you have 2n, take out a 2 from the last, and then you divide by 2 because, right, a round has 2 games.
Okay,
Okay,
got it. Thank you.
sure. Okay. What's the probability that A will win?
So I'm kind of thinking back to that other problem with the four heads and like the tail and then three heads. So if it's like the same concept, it kind of resets every time it's um like A and B or B and A. So I think it would just be P squared. You just have to consider the chance that um A will win twice.
No, it's not connected to that problem. I don't think so.
Okay.
Right? That problem is really about how a pattern will come out, and if you have a certain kind of outcome, then it's fixed that the pattern head will come first. Here is a very different kind of nature where, right, you see that the game can continue on, technically speaking, forever, right? And in each of those two end outcomes, A can win with some probabilities or B can win with some probabilities, right? But we want to ask, what's the probability A will win, period, without any specific length. For example, right, if you want the probability A would win in, let's say, A points, then you would use this answer with n equals to 4, and then you would take P squared, okay? This is a probability A will win in 8 points, all right? Exactly 8 points. Now, of course, you can also phrase a question as, what's the probability A will win in 8 points or less, which is going to be the sum of everything leading up to that. But we want now the probability of A wins, period, without specifying number of points. That's the challenge of that question.
Would it be p squared over p squared plus 1 minus p squared?
That's an excellent answer. And where does that come from?
Because like before the last two deciding rounds, um like before then, all of like every 2 points you play, you have to reach your drawn stage, and every drawn stage is like equivalent to the initial stage. So essentially, you just have the last two deciding rounds left.
Well, that's an excellent explanation. But let us, no, I mean, what you said is perfectly good. But let us cast this right into a concept that we have seen before, right? Does this expression look familiar? This looks like a conditioning, right? Probability. So how come? How come, right? The probability of A win comes out to be something like a conditioning probability. And that's exactly the relevance of this question, right? In this section, right? This lecture, this part, right? It's not about part A. Part A just meant to kind of let you explore the structure of the game. Part B is really the relevance. But why is there a conditioning in here? While the question, right, really has no conditioning in it, at least not explicitly.
I guess you can think about it, the probability of A winning, you can consider both of them winning. So it's like the probability of A winning giving that A or B wins. So that's how it turns into that expression there.
Good. So that's exactly probability of A wins given A wins or B wins. But let's kind of continue more, right? Where does this come from? Or have we analyzed this structure before?
Well, there's two outcomes that could happen. Well, I don't know how to phrase it exactly, but we know that we're focusing on the idea of winning. So there's two outcomes that can happen, A or B. So if we know that one of them is to win, we can kind of write it as that kind of conditional probability.
No. Actually, that's incorrect, right?
Oh, okay.
Because I mean, if you do that, and so actually here when you do that, right, you have to be careful here. It's not really A wins because I mean, for example, right. Let me just give you a explanation. What do you think probability of E condition on the whole sample space is?
Just E. Probability of E.
Correct, right? Because the whole sample space doesn't give you any extra information. So if you're not careful, what you're saying here turns into that, right? Because so what you're saying is like, well, P of A wins, right? So you're not putting extra structure into this question, right? What your friend said actually is slightly different. He didn't quite say A wins given that. What was he focusing on? He was focusing on the last round, right? So this is not wins as in win a game, wins one round, one round, one round. Okay? Because, right, otherwise, if you say A wins or B wins, clear, of course, either A wins or B wins, but then you will condition our whole sample space and we're not doing anything, right? But then where does this come from? This looks like, let's say, P of E condition E union F. And we did talk about this structure before. Remember when? This is the probability of E before F, right? So what your friend said was perfectly fine, but here's another way to cast it into the language that we've been discussing before. So basically, right, the game can be viewed as A and B keep playing rounds, right? And a round here, by a round we mean a set of two games, right? And they keep playing until what? They keep playing until one of them win a round, right? Because then they will win the whole game. And that's what he was saying about keeping draw, right? The draw basically reset, right, the game. Right? A draw reset the game. So you just keep playing, right? So you keep playing until you are in this event, right? So that's why you condition on that. And when you're in there, right, what's the probability you see that AA rather than BB? Or, right, kind of basically, if you want, another way to say this is probability of A wins a round before B wins a round. Does it make sense? Which comes out to be this answer. So that's the relevance of this question in this lecture. Any question on this? All right. Let's continue. Okay, so this one is rather easy, actually. Probably just have to kind of look at the wording a bit carefully, right, to see what they're asking. That's all. It's not as difficult as question number one. Okay, so seems like we have something like D, right, for dog, and C, right, for a cat, right? Something like that. And so let's interpret, right, these statements. Okay. So this 36%, right, clearly means PD is 0.36, right? How do we interpret 22? What is that statement?
Probability of C given D.
Yeah, I would agree, right?
22.
Right, that's P of C given D. Do we agree? That's the point there. So if you know they owns a dog, then right they will own a cat with the probability 0.22. All right. And then P of C, right, is 0.3, right? And so part A is P of CD, right? Correct? Which would be what? P of C given D times PD, right? And there's that. Agree? And B would be P of D given C, right? Which would be P of CD given P divided by PC, right? All right, you fill in the blank. Is that okay? Any question here?
Wait, yeah, this like the formulas make sense to me, but for some reason I'm thinking like they own a dog and also own a cat. That kind of sounds like the same thing as C and D.
Which one, A or B?
Um, well, I guess A, but I'm in my head like if they own a dog, then they also own a cat. That's a probability of 0.22 we're saying, but I think I'm
So
confused. I'm thinking that that also means like the probability of C and D. How is that different?
you're asking comparing this statement, right?
Yeah.
And then this statement, right? Correct?
Yeah. Yeah.
So that's exactly what the slide of P of E given F versus PEF about, right? And well, I did say, right, you're bound to get confused. So the confusion here is just really about interpreting the statement, right? And see which one is which. So the keyword for P of EF is what? The keyword for this one is
And
and, right? So from that point of view, I think at least it's pretty safe to say that part A is and, right?
yeah. Okay, wait. I don't know why. Initially my intuition was kind of like confusing me, but I think I see the difference now. It makes more sense to me.
No, it's exactly that point, right? That you might know it, and then you will get confused, and then you will go back. This is exactly why you have to be very clear on what the distinctions are, right? Otherwise, yeah, I mean, I would agree. I see exactly why, right? But that's it. You have to kind of distinguish. And the reason here, right, that this should be interpreted as a conditional statement is, right, I would argue that the way we parse the statement is if, right, the family owns a dog, then it's 22% that they owns a cat, that they own a cat.
Yeah, what helped me was kind of like narrowing that statement down to like we're only looking at families that have a dog that have a probability of having a cat. But thinking about like E and F, that's like the whole
But
probability space, if that makes sense.
yes and no, because the word narrow actually is a vague word. EF also narrows F into E, right? So the word narrow there is a vague word that could mean either way, in my opinion, at least.
Yeah, yeah,
Okay.
I see what you mean. Yeah, I agree.
No, and then yeah, again, right? You have to you find your own way. But from my experience, if versus and, past versus present, given versus not given are the clear ways to distinguish these two. Okay. The narrow could dangerously steer you in both ways. Right. Any other question? All right, let's see if the solution agrees with us. Yep, right, exactly. I mean, this is my solution, so well, I wrote it a long time ago, and I do not check the solution before I go to class, right? Just to make sure that I'm still sane. So, all right, let's look at this one. Okay. So again, right, this is one of those where you just have to parse the statements, okay, and the questions. So what do we have? We have females and males, right? I guess that's the first thing. And then we have CS. Well, let's see, right? So what is it? 52% are female, right? So P of F is 0.52. I think that statement is straightforward. 5% are majoring in computer science, so P of CS is 0.05. Right? That's also straightforward. Then what? 2% are women majoring in computer science. How do we parse this statement?
Probability of FNCS is 0.02.
Correct. Correct. This is FNCS. Correct. Right. It's not any given. Right. Good. And now, right, we have to find the conditional probability, right? Blah, blah, blah. PF given CS, right? Which is, I guess, FNCS over PCS. So that's it, right? P of CS given F. Again, P of CS and F or P of F. All right. So once we have that, everything else is clear. Any question? Okay. So this is probably a classic one for the Bayesian formulation. Pretty easy, right? Take a look and then we'll solve it. Okay. So there's no requirement here, but right, a tree would be helpful here, right? So where do we start the tree? With what event? Your tree would start with what? The weather or late? The weather, right? So 0.7, 0.3, and then rainy day. So late, not late, right? That's 0.3, 0.7, and then 0.1, 0.9, right? So I guess not late is early, right? So P early would be, right, the sum of these two branch, right? Correct? And B, right, given what that we're on this branch, probability that you're on the first. So really it's the relative weight of the first over the total sum. Okay. Any question? All right. And there we have it. That was the last problem, right, for this worksheet from set 4 part 2. Right, any question before we begin the new material? All right.
Professor, wait,
Yep.
sorry. It was kind of my mistake. I guess I didn't really completely write down B for question 2. I don't know if you're like allowed to go back to that so I can see what I missed or if I just missed it and that's it.
2. You mean this one?
Yeah.
Okay.
Okay.
The 2 was discussed last time. We
Yeah,
went over it last time. Yeah.
yeah, I don't know. I just missed part B. It's just not. I wrote down part A in the explanation, but
Sure.
if I could just try to understand this for a second.
So part B was
Oh, right.
given that
Okay.
she did not pass, so she's on one of these 3 branches. And then you asked for she being on not on this branch. So it's
Yeah,
this.
okay. Okay, sounds good. Yeah, I see what happened. All right, thank you.
Sure. All right. We're good. Okay. So let us continue with the new materials. All right. So in terms of where we are, in terms of the materials, the scheme of things, again, right? I mean, different textbooks like to do this differently. A very logical scheme and time-honored scheme is that we start out discussing, sample space, outcomes, events. Then you learn a lot of probabilities. You learn how to manipulate, right, probabilities, and then conditional probabilities and things like that, right? A bit of combinatorics get thrown in so that you can calculate probabilities for equally likely, right, outcome sample space. Okay. And that's that, meaning that after you finish that, what you have learned to do is kind of, I mean, at least in theory, you should know how to calculate probability of events, conditioning, that kind of thing, right, for events. Okay. And that's great, right? That's really a lot of probabilities already. But one thing, right, that I guess will be missed out on, and one thing that is a major part of probability, right, is the notion of random variable. Okay. And so that's where we are right now, right? So after we discuss events, then we will, and probable events, now we will move on to discussing random variables, right? So we're in like sort of like the second half-ish of probability, even though you see there's going to be a third portion. So like, let's say the first 1/3, second 1/3, right? The last 1/3 is like a more advanced topics in random variables and things like that. But so random variables is like a special concept, right? That needs to be explained and laid down before we can do math with it. just like events and outcomes. So you can view this lecture as like the equivalence of lecture 1 in some way, like laying down the framework, right? But there will be math here, right? So basically, right, when you look at an experiment with outcomes, but the outcomes here have numerical values, right? Like, rolling a dice would be natural, right? You have 1 to 6, the time, right, that the bus arrives, right? Number of customers arriving at the store, etc., right? So these are experiments that somehow when you name the event, right, you have a number attached to it. For example, the event that the bus will arrive, before half an hour, or the event that the 5 customers or less arrive at the store. Basically, there's numerical values attached to this. On the other hand, there are events that doesn't have numerical values attached to this, right, naturally. For example, when you toss a coin, right, or whether things will rain, things like that, right? There are events, we understand them enough, we can attach probability on them. They just don't have numerical values attached to them, right, naturally. So informally, because, well, if you want to do it formally, that's the topic of a course called measure theory. But informally, a random variable, the topic here, is basically ways to assign numerical values to events, okay? So basically, not all events have numbers. You want to assign numbers to events that will turn them into random variables, okay? In a way. Now, of course, right, for example, here, when you assign numbers to events, you can even change the numbers that inherently associate with the dice, for example. Dice rolls 1 to 6, no reason why you cannot look at it as 2 to 12, okay, by multiply things by 2, things like that. We'll see, right? But for now, random variable is just a way to assign numbers to event, right? So right here, right? For example, so if here we look at the examples that naturally have numbers attached to them, okay? Roll a dice, time the bus arrives. Also, Y is, time the bus arrive, and number of customers, right? So first of all, notice, right, we use capital letters, but at the end of the alphabet, the X, Y, and Z, capital letter, right? These will denote random variables. While capital letters as well, but at the beginning of the alphabet, E and F, they will denote events, right? So basically, right, when you look at the random variable and you look at the event that they take on some values, then these are events. So these are old stuff. But basically, this is not really saying that, well, these are old stuff, but these are the way to say new stuff is connected to old stuff by this action. Basically, when you look at a random variable and you look at, right, them taking on certain set of values, that will become a random event. Okay. Any questions so far about this? All right. So if you feel like, right, well, it seems like I was discussing the same thing somehow, you're not wrong. I mean, if again, you're not experiencing this, it might sound like I'm discussing the same thing. I assure you I'm not. But right, they might be right. Seem confusing. The reason is they have connections, right? They have deep connection. So close connection, right? If you have a random variable, right? Basically, you can think of a random variable, right? To be blunt, is something that takes on numerical value randomly. Let's put it that way for now. Okay. So that's sort of like the punchline here, right? An event cannot take on numerical values, right? Because event is event. But random variables are something that take on numerical values randomly. And our task is to look into those numbers and see what meaning lay behind them. So there, right? So if there's something that takes on numerical values randomly, then if you look at, right, the event that the values lie in a certain range, they are random events. Okay. So basically, right, yeah, from a random variable, you can turn them into random events, turn it into a random event by looking at, right, the event that the random variable take on certain range of values. Conversely, if you have a random event, you can always associate a numerical value to it. And the easiest way is to say that, you know, I assign 1 to the event E and 0 to the event E complement. Meaning, right, that I have a random variable that takes on value 1 if E happens, and 0 if E does not happen. Okay? This will be called a Bernoulli random variable that we'll look at in next lecture. So you also can just look at this, you know, the gambling way, right? For example, right, what's betting? You see, betting actually is probably the most intuitive way to explain a random variable, right? You could bet on anything, right? You could bet on whether it's going to rain tomorrow or not, right? So when you do that, you associate a numerical value to this event. Because, right, if it rains, you get paid so much. If it doesn't rain, you get paid so much, or you lose a certain amount of money, right? So you associate money with these events. Of course, you can, you know, fine tune these events to even more, right? For example, it rains at 4 o'clock, etc., etc. But however you bet and different betting schemes, right, are different ways, right, to assign numerical values to event. So that's probably the easiest way to imagine or visualize a random variable. Okay. So there, right? So notice that head and tail naturally, right, don't have numerical value associated to them. But you could associate 10 to head and -5 to tail, and there you have it. You have a random variable that has 2 outcomes. All right. Any question about this? All right. So there you go, right? That's exactly what I was meaning when I say this. So we say something is a random variable, then what we mean is it takes on numerical values randomly, okay? More formally, if it's a random variable, then you can assign probabilities to all these events. They're all well-defined, okay? However, right, notice that you can talk about the probability of these events, but there's no guarantee, at least, you know, abstractly, or yeah, that these events doesn't have to be empty. If you're not careful, right, and if you choose a certain values and you look at certain kind of event, that event associated with that random variable could be empty, right? For example, if you look at the roll of a dice, first of all, right, notice this qualifies as a random event. All right, it's valid. It's just a trivial one. It's an empty event. Okay. Same thing here. This is also valid as a random event. And by the way, right, you can see that x less than or equal to 1,000 as a roll of dice is valid as a random event. But it's just not a very interesting event because that's a whole sample space. Do you understand? Any question on this one? All right. So, right, this is kind of like, again, the notion of random variable is very important. So we're just kind of repeating it in different points of view so that you get it. So a random variable, right, like I said, is a mapping, right, a way to assign numbers, which is the real line right here. I mean, in this class, we only look at real valued random variable, but in general, random variable can be complex value, meaning, you know, imaginary numbers, It can be a vector value, right? But forget about those things. For now, we're just going to do real value random variable. And right, so it's assigned real value from the sample space, right? So here, I kind of like switch notation here, right? Omega, that's our S, right? That's our usual S. So basically, right, when you look at the values the random variable can take, implicitly describes the outcome of the sample space. So basically, right, the point is, right, for example, you look at the random variable taking on value 0 and 1, right? That's like a coin toss, but you're not really implicitly, oh, sorry, right? I guess I switched things here. I should say it's 0.5, 0.5. Sorry, I just prepared this slide, so there's typo here, right? If I look at this as 0.5, 0.5, right, then I implicitly are talking about a sample space with two equally likely outcomes. Okay, so like that, right? Basically, random variables implicitly define a sample space, right, by looking at the values those random variables take with the probabilities it can take. Okay. Any question here? All right. And right here is another thing. Basically, right, unobservable is one way to put it, but it's also not spelled out. It's more of another way to put it, right? So for example, here, when you say 0 and 1 like this, you're not really naming out the sample space, right? It could be a coin toss, could be anything else. But notice that again, right, x equal to 0 and x equals to 1, right, turns out to be the two outcomes of this sample space, right, like that, right? So whatever is behind the scene is not spelled out, just the value, right, the random variable can take, the values. Okay. All right. So now we go to this important concept of the support of a random variable. And this, right, just like, outcomes in sample space, right, is a favorite part where students love to skip when they look at a problem, right? When students look at a problem in calculating probability of an event, they would love to just write down the answer, right? And do not want to think about what sample space we're looking at. Same thing here. When you deal with random variables, it's my experience that students would love to just jump in and get to the answer or something and don't even look at what values, right, the random variables can take to begin with. Which, by the way, right, is understandable, but it's not a good habit because it will not lead to a good picture of what's going on. And it will hurt, right, in the end if you miss out on some fine details, right, or whatever. So this consideration should always be done when you look at a random variable, especially the ones you don't know about. And so, right, the values the random variable can take. And exactly, right, this is the outcomes of the sample space that we talked about up here, right? So, right, if you have a roll of dice, easy, right, 1 to 6. If you have rows of, if you roll until you see a 6, okay? Notice. So one thing that happens is that we don't have that many letters in the alphabet. So we end up recycling the letter X, right, for a random variable. But X can stand for many things, okay, that are different. Oh, sorry. Okay, sorry, it's time. So let me stop here. Let me give you the quiz and then we'll continue after the break. So, all right, is it okay for everyone to see this problem? Right, this will be the quiz. All right. Okay. Any question before we take a break and begin and start again at 7:05? All right. So Okay, let's continue. Is there any question before we continue? All right. So right. So we were discussing, right, the concept of the support of a random variable and how this is actually a very important question, right, to be asked about any random variable before you work with them. And so here are some examples, right? And we were discussing how, right, then even though we use the same name, right, it's just sort of like unfortunate. Well, whatever, right? But we can switch the names if we want. But anyway, right? But the meaning of these are different. For example, right? Here in the second example, this has a meaning of time, right? Because when you look at the number of rows until you see something, that's the time you wait until some event happens, or in stochastic process is referred to as a stopping time. All right. And if you look at this one, right, this is the number of customers arriving in 1 hour. And one thing that you should distinguish between, let's say, 1, 2, and 3, right, and we'll look at 4 later, is that there are very difference. There are differences among them, and there's subtle difference, right? The first most obvious difference between this one and this two is that these have no upper bound, right? So basically, the support here is infinite for both of these random variables, while the support here is finite for this random variable, right? And random variable with finite support or infinite support, well, I guess you have to deal with them. You have to kind of be a little bit careful, right, when you deal with them, because, for example, kind of implicitly behind these two are some sort of infinite series, right? You have to deal with. Well, there's no infinite series for the first one, for example. Second, right? Notice that this one starts at 1, right? 1, 2, 3, and so on. Well, this one includes a 0, right? Small but significant, all right? Because if you miss this 0, that's incorrect for this one. Why? Because it's a number of customers. So, right, no customer can arrive. That's possible. While if you include a 0 here, that makes no sense because, right, you need to at least have a row before you see a 6. All right, things like that. And so in terms of names, right, these are not just kind of some example we pull out of the thin air. This is called a geometric random variable. This is a Poisson random variable. This is a, well, just a dice toss, but you can also call it a discrete uniform random variable, right? And so we're discussing basically the support of well-known random variables or well-known distributions, right? That we'll look at in the next lecture. Well, the last one is slightly different in which sense? Right, here is the time too, but notice this is time in the discrete sense, right? Time, the number of time it takes, that kind of thing. Here, this is time in a continuous sense. So you see that the support here is a continuous interval. Right? While these 3 are discrete values. And that actually set off, right, the distinction between 2 worlds that we'll be looking at from now on a lot. Discrete random variables versus continuous random variables. They have slightly different techniques, slightly different ways to deal with, okay, that we have to look at. All right, any question about this? All right, so let's take a look at the problem. All right, to show you, hopefully, that, right, support doesn't have to be an easy question. So let's take a look at that one. Okay,
Is this referring to the absolute value of the difference or a particular like number of heads minus number of tails?
just the difference, right? If it's absolute, there will be a
Okay.
word there. So if you trust the question is meant what it meant means, then no, right? It just means a difference. So it is like that, right? We have to interpret the question the way it's supposed to. Yeah, no absolute here. Okay, so what's the answer? What's the support here?
I would say it's like discrete uniform from negative n to n because you could have like if it's like heads
Well,
minus.
it's discrete, yes. Be careful with the word uniform. Uniform has
Oh,
a strong meaning there, meaning the probabilities are all the same. I don't think so. At least doesn't seem like that.
oh,
Uh,
okay.
yeah, the
I
word
interpreted it
uniform.
as just being like the same difference in
Yeah,
like
yeah. That
distance.
the word uniform has a special meaning. The reason why it's uniform here is because I kind of refer to a fair dice, so 1/6 each. We'll look at that. Yeah, so discrete is fine. Don't drag in the word uniform. So, but anyway, right? What you're trying to claim is minus n plus one, minus n plus two, etc. 0, 1, 2, etc. up to n, right?
Yeah.
Do I understand you correctly? So yeah, right. So notice here we're only looking at the values, right? We're not looking at probabilities yet. That's a question later, right? So yeah. Okay. Any questions here? No question. How you know the answer is correct when you look at it?
Uh, I think I might have a question.
Yeah. Go ahead.
Um, sorry, I think I need a little bit.
Yeah,
But
that's fine. Uh-huh.
I think like there's less than this like the set as shown here.
Yeah. Why?
Because like if like let's say you start with all of them are heads, and then if you flip one from heads to tails, you're essentially losing two, right? Because you lose a head and you gain a tail, so the difference is changing by two.
Yeah, that's an excellent observation. Excellent. Correct. So basically, right, again, this is just to show you that, right, something you think is, yeah, looks like it, should be like it, blah, blah, blah. Eh, okay. You have to think about things very carefully. So let us kind of, right, look at it like this, right? Yeah, correct. So let's just try to be concrete. Let's say n equals to 3, right? Let's say a coin is tossed 3 times, right? So what possibilities do we have? We could have 3, so this is head and this is tail, right? 3, 0, correct? And then if we have 2, then we would have 1, right? And then we have 1 and then we have 2, right? And then 0 and 3, correct? Those are the only possibilities, correct? And so, right, what are these? 3, 1, minus 1, minus 3, right? Want to try again? Let's say 4. What was this? 4, 0, 3, 1, 2, 2, 1, 3, 0, 4, right? 4, 2, 0, minus 2, minus 4. So, right, what should the answer be? In fact, you see, must 0 be included in the bound in the support? Must this random variable always take value 0? No. Right? Why? Actually, the reason is pretty obvious when you think about it. If a coin is tossed an odd number of times, x equal to 0 means what? Number of heads equals number of tails. But if it's tossed an odd number of times, could that happen? Nope. Right? So again, I'm not saying that this answer is terrible or anything like that. It's really actually good in the sense that it demonstrates a natural answer you would want to have. But if you don't think twice, you could get it wrong. Right? And the consequence down the road you can imagine might be severe. As in you will search for some value 0 here and work with it while it's non-existent. You understand? Is there a question? All right. Let's try this. All right. So this one should not be that difficult, maybe. So the maximum of, right? So you can call it x1, like x2, taking value from 1 to 6, right? This is in, right? So I'm merely talking about the support. So the first one is max x1, x2. And this is actually a notation, right? You take the max of two random variables. That's what you mean. So what values can this take?
Just 1 to 6.
Yeah, right. Nothing crazy there. Except that you might want to think, right, for the extreme case, how that can happen. But right, clearly 6 can happen if one of them is 6. 1 can happen if both of them are 1s, right? Things like that. The min, well, it's also 1 to 6. Agree? The sum will be from where to where?
2 to 12.
All right, good. D would be x1 minus x2. And this would be? And by the way, right, I guess inherently the dot 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 here is consecutive, right? You know, I think that's the default read, right? So when we say 1 dot dot 6, we don't mean any special gap. If you want to express a special gap, you probably want to tell people in some way like that. Yeah. Okay. So the difference. What values can I take?
-5 to 5.
Any special gap?
No.
That's correct, right? For example, right, how can you achieve -4, 2, and 6, right? So it's consecutive. Is that okay? All right. Any question? Okay. So here is a continuation of the previous one where, right, sort of giving you a precursor, right, to what we'll be discussing or what will the theme, right, of a lot of things we'll be doing next, or when you learn statistics or whatnot, that this is a recurring theme. Discrete versus continuous random variables. Okay, so discrete random variables basically take on discrete values with positive probability. All right, like a dice throw. That's sort of probably intuitive, and no one would question this. The continuous random variable is where things get not easy for some. Basically, a continuous random variable is a random variable that takes on any particular value with zero probability. All right, but that doesn't mean it's sort of like empty or something like that. Basically, right, probably x equals to a is 0 for any a. However, something like this would be positive. Probability is less than a will be positive. Like here, these are positive quantity. Even though probably x equals to a equal to 0. All right, if you want to look at the bus experience, right, it's like this. Or here's a demonstration for you. If you look at the interval 0, 1, right? And if you look at a needle, and I mean a needle that is not physically possible, a needle that is atom thin, right? Because this needle has to hit a point and a point only. And let's say that you drop this needle uniformly between 0 and 1, right? And you call that x, right? That x is exactly the needle that you drop uniformly, U here for uniform, between 0 and 1. What do you think the probability that you will exactly hit on 0.5? The answer is 0. Okay. However, what's the probability that your needle will be dropped before 0.5, meaning to the left half? Well, if you move it uniformly, the answer is 1/2. That's continuous random variable for you. You understand? Okay. And to demonstrate to you that this may or may not be easy to digest, at the end of the spring semester, the recent one where I taught this course, where a student basically finished taking my class, a student sent me an email asking, well, why is it that a bus, because I like to use this example for bus, right? The time that the probability that the bus arrives exactly at, like, let's say half an hour is 0. The student doesn't believe so. The student thinks that it should not be 0 probability. All right. And my response is simple. If the students go to the bus station and the bus ever arrives exactly at the half-hour mark, whatever that means, right? I will buy the student lunch for the rest of the year. And you know why, right? So the confusion, right? Or the whole point is you have to be very precise in math. When the student or you guys, right, think that the bus arrives at half an hour mark, at least in your mind, you subtract 1 or 2 seconds, plus minus. Agree? In fact, right, the event that the bus arrives exactly at half-hour mark is a physical impossibility. You think about it. You cannot even measure, right, the bus arriving at exactly half-hour mark. Do we understand? Because here, right, the tricky thing is exactly the continuum here. Okay, the continuum here. And without you guys having taken a course in real analysis, I cannot push further into the explanation. But there's a idea here about uncountability. That's sort of behind the scene, right? So in contrast with something like this here, this is infinite but countable. This is infinite but uncountable, okay? And that's why, right? And again, like I said, right, time as you think about, like continuous time, right? As we conceptualize about, you will never really you can never really catch a exact moment, like half an hour, things like that. You will never do that. You can catch it at least a split second after or something. You have to have an error. And that's exactly capturing continuous random variable. All right. And so continuous random variable needs a special device to work with called the density. All right. We'll look at that later. Any question about this? Okay. So let's go back to this remark. For a continuous random variable, then this and that are equal. Right? We see why. What's the proof? The proof is this is equal to this plus that. Correct? But if a random variable is continuous, then this is 0 for any value. Okay? So in a sense, right, for a continuous random variable, open interval and a closed interval means has the same weight to it, has the same probability to it. But be careful, all right? A discrete random variable will not behave in the same way. This will be different. Why? Because the same, right? This is true by logic, right? However, right, for a discrete random variable, this is positive or could be positive, right? So this, by the way, right, if it has a weight, it will be called a point mass, right? Literally like point mass in physics, right? So discrete random variables have point mass. Continuous random variables have density, but no point mass. Is this okay? These are abstract concepts, by the way. They are not that easy to get right. So do ask questions. Okay. So, right, for a continuous random variable, then you cannot really talk about it taking on a particular value. Then, right, you talk about it being in some intervals. Okay, that's the point. That it's not like because it take on a particular value with probably 0 and you stop talking. No, you do, but you talk about it being on some intervals. Okay, but for discrete, then you talk about it taking on some particular values. Okay. Now this is advanced, and we will only have one problem, right? Maybe one problem in this course that deal with this, but it has to be there because one illusion. I mean, there are many illusions you can have throughout a probability course. One favorite illusion of mine is when a student take a weird probability course, they think that everything is discrete, meaning that they take a course where the only thing they see is discrete random variables. So that's an illusion that is weird. But you can take a course that discusses both worlds and you still have an illusion. And the illusion is things are either discrete or continuous, which is understandable because, right, that's already a lot. But no, all right, things can be neither discrete nor continuous. All right, but advanced, as in, like I said, you won't see this as much in in this class, right? It's kind of more for stochastic process and things like that. But you can toss a coin, right? And if it's head, then you take value in 0, 1, continuous. If it's tail, you're just exactly 2. Right? You see that because it blend these 2 together, it's neither discrete nor continuous. Okay. So we do not consider these, well, sorry, that's not super precise. There's one problem that we'll deal with this we'll explain, but that's it. It's not common in this course. But keep that in mind as you graduate away from this course and do more advanced stuff. Okay, any question? All right. So now let's move on to, right, the idea of what you need to know about random variable, right? So this is kind of similar to what you need to know about sample space. But you don't get to see this as much in the sample space that we've been discussing. The reason is we mostly stayed within the equally likely outcomes. Therefore, it's almost trivial, right? That it's 1/n each, or you just do counting, right? But for a random variable, right, you can see that things are much more interesting. At least things don't have to be equally likely or uniform here, right? A dice toss will be equally likely. But I hope, right, it's intuitive that none of the examples here, these 2, right, are equally likely, right? At least intuitively, right, it's harder or it's less likely for more customers to arrive, right? Well, I'm not so sure, maybe. But at least, right, the numbers here don't have to be the same probability. It doesn't have to have the same probability, right? And here, this should be clear, right? Is it? That, yeah, right? The higher this number is, right? What does this mean? The higher this number, the higher this number is. What that means is you will toss a lot of rolls before you see the first 6, right? So, for example, if this number is 10, that implies that you will toss 9 dice toss and do not see a 6, and on the 10th toss you see a 6, right? Again, intuitively, hopefully you feel like that's kind of more rare. So the point I'm trying to say is that not all of these are equally likely, right? So that's why you want to, right, be able to completely characterize a random variable before you can work with it. That's like the ideal, but most random variable, right, you work with, you kind of want to at least get to that point, because otherwise is you don't know much about it, you cannot work with it. So you completely characterize a random variable if you can know the probability of all events associated with the random variable, right? So basically, you can answer any questions that pose about the random variable itself. Well, but notice, right, for a random variable, there are too many events, right? A lot. For example, events of these types, right? So we break it down to a simpler characterization. If it's discrete, then you completely characterize it if you know the probability it takes on all values in this, right? And you know everything about it. For a continuous random variable, then you completely characterize it if you know the probability is in any intervals, right? So again, for a continuous random variable, this sounds like a lot as well. But as you will see, right, those are the so-called direct characterizations, meaning that they're kind of like the most obvious things we want to say. But with math, right, there are sort of indirect ways to describe these random variables. That's sort of like the last third of the course, right? Basically, there are ways to describe the random variable in the abstract that somehow entails or encode this information in that description, okay? And that's the topic of moment generating function, which we'll be discussing at the last part of the course. But even for continuous random variable here, right? There will, as I mentioned, there will be a density function that actually will be the characterization of it. So these are like the most blunt way to describe it, right? Because you want to look at an event, you want to know its probability. But density will be, let's say, an abstraction away from that. That will, basically, if you're given the density of a continuous random variable, then you can calculate these probabilities for yourself. Okay. Any question about this? All right. So, here comes a notion that tends to be skipped over in, I guess, in the student's mind mostly. So here's the thing, right? One way to motivate the CDF, or cumulative distribution function, is that notice, right, the above description right here, right? Discrete, continuous, indirect, blah, 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 right? There's just way too many variations. I mean, not too many, but you can make that complaint. So the CDF is a unifying way to characterize a random variable. Meaning that, right, you could say, and no one can fault you for it, that if you're given the CDF, or the cumulative distribution function of a random variable, then you completely know that random variable itself. This is an advanced concept, okay? But it's actually the cornerstone of probability, so we must talk about it. And second, it's not just that in terms of theory. In practice, as you see, this CDF will play a big role in continuous random variable. In discrete random variable, you can stay away from it, or you don't have to talk about too much. That's again a reason why like most students don't know the CDF that well, because they tend to drill more on discrete for some reason and neglect the continuous. Okay, but this is a very, very important idea, and we'll hop on this to the extent we can, okay, in this course. So first of all, right, CDF, or cumulative distribution function, also called distribution function, is really a simple definition, right? It's basically the probability, right? So first of all, so this notation, we'll get used to it, okay? So there will be three components to a description like this. This describes the function itself, so big F for cumulative distribution. X here, right, does not denote partial derivative like Cal3, all right? I mean, it's just a subscript, but it denotes membership. Meaning this is F as a CDF of the random variable X, okay? So it's referring to random variable X. Why? Because there are occasions where we have to look at two random variables at the same time. So we will look at the cumulative distribution of the random variable Y and the cumulative distribution, the CDF of the random variable X, right? So that's there for that reason. And then finally, right, A here is where it's evaluate at. Okay. So this is the CDF of X evaluated at A, right? Try to say that 10 times, okay? And so again, what it means is just look at the probability of X, that X right there, being less than or equal to A, okay? That's it. And as you range over different values of A, then you get the whole CDF function, CDF curve. And again, right, if you know the CDF, then you know the random variable itself. Okay, and we'll have an example to describe this. But first of all, right, let's kind of, we'll talk about this, right? Let's explain why this is true first, right? To kind of like at least convince you that the CDF is relevant. So why this statement? This statement only makes sense, right? If somehow the CDF allows you to recover the information above, correct? Because the above, right, is or are, right, the most direct way to know or to characterize a random variable. So if you claim that this allows you to do the same thing, then you better be able to recover at least this information from the CDF. Okay? And can we? Well, let's take a look. Right here. Right? These are actually what I will talk about, right? These are both identities about the CDF that you must know about, but also, right, they explain how you recover, for example, this from a CDF or that from a CDF. All right, so let's explain this. But for one thing, right, the CDF has the equal to here, all right? Without the equal to, that's not a CDF, but the left limit of the CDF. So here, probability, I guess, let's put it here. X less than A is a limit as X goes to A from the left of the CDF, which is also denoted as that. Okay, maybe I should put that there as well as an identity. Okay, but let's go over this. Sure, any questions before we explain these statements? All right, so this is definition of the CDF, right? This is complement, right? What about this? Well, this you can see, right? Probability A less than X less than equal to B is probability X less than equal to B minus probability X less than equal to A. Agree? Because the open interval, I guess half open close, will be minus infinity B, but not minus infinity A closed. That's a set notation. All right. And finally, right, this we explained, right? Like that, right? So less than equal to and strictly less than. Okay. But the thing, right, is that for a random variable, right, these don't have to be equal, right? These don't have to be equal. And so that's why, right, for the strictly less than, you have to approach the CDF from the left, right? Basically, you are looking at all values less than A, but close to A, right, from the left. You see, if X is less than A, right, here's A. Less than A is exactly getting close to A, but not equal to A. So that's why you're approaching A from the left, and you will capture all probabilities. That is, right, close to A or less than A, but not exactly A. Do you understand? Okay. Any question? All right. And so right now, let's explain the CDF. So a CDF, right, being this definition cannot be arbitrary. It must have certain properties. So I guess the first thing is just, it's defined for all random variables, right? That's why it's a unifying tool to describe random variables. Anything, any random variable. But the first thing is that the CF is increasing. Okay. So if you ever plot the CDF like that. So this is X, right? This is F. No one has to even look twice. That's nonsense. Okay. Why? Why, right, is of course because of probabilities, right? X less than equal to A is contained in X less than equal to B, right? If A less than equal to B. So therefore, right, remember this is the axioma probabilities on day 1 or day 2 of class. Probability of this first set must be less than equal to probability of the second set. Okay. So that's wrong. Oh, well, I guess this implies that too. But right, if you want to spend another line, then the CDF must stay between 0 and 1. Right, the value of the CDF must stay between 0 and 1. So in other words, it cannot go above 1 and it cannot go below 0. Is that obvious? Yes, it is. Reason? Because CDF value, right, is a probability, right? So that's why it must be between 0 and 1. So it's increasing between 0 and 1, right? And so probably intuitively it does what you expect it to do, meaning it's, roughly speaking, starts from 0 and rise to 1 asymptotically. That's what it says, right? To the right, it approach 1. To the left, it's approach 0. Why? Well, the Y, right, is again by definition almost, right? If you look at this, right? So this here, it's just really also A, right? If you push this value all the way to infinity, so, right, you see that basically any random variable, if you look at a probability, it's less than or equal to 1 billion. Well, that's going to be a big number, right? It's very likely that a random variable is less than or equal to 1 billion. Okay, fine, your random variable is even larger, but then you can push, right, the number larger and larger. Remember, this limit is going to infinity. So eventually, right, it should capture all values a random variable can take. That's why it's 1, right? But similarly, if you push the value to the left, right, all the way to negative infinity, right? What's the probability that your random variable is bigger than minus 1 billion? And well, that should be pretty large, right? Sorry, smaller, right? What's the probability that your random variable is smaller than minus 1 billion? Not likely, right? Okay, your random variable can be very negative, but then if you push it all the way to negative infinity, right? Then the probability will be so small that it's approaching 0. Okay, so this explains the statement. So in other words, right, whatever CDF you draw must start from 0 and rise to approaching 1, right? But of course, it doesn't have to cover the whole range of minus infinity and 30. Okay. For example, let me see if I ask here. Let's do this, right? Let's look at the X random variable, right? That takes on value 1 to 6, right? Where probability X equals to, this is 1/6 each, right? So this is a dice toss, right? So the question is to sketch the CDF of X. All right. So you don't have to sketch it out explicitly, but tell me, what would this graph look like? Meaning, right, you want to plot the probability X less than or equal to X for all meaningful values of X. right? So how would that look like? Okay, let's try. So here's 0, right? What happens, what value is this to the left of 0? To the left of 0, what's the value?
That would be 0, right?
Yeah, right, probably x less than equal to x for all x negative will be 0, right? That's clear because it takes value 1 to 6. So the graph of this will be 0, like that, right? To the left of 0. Okay, now tell me. Oh, okay. Actually, right, it's 0 up to what? Up to 1, right? In fact. Agree? Because it takes value from 1 to 6. So the probability is less than equal to any value less than 1 will be 0. Right? Now tell me what happens at 1. What's probably x less than equal to 1?
You jump to 1/6?
Correct. Excellent. So you see, there's a jump, and that's the right word. There's a jump to 1/6. Okay? And now what happens between 1 and 2? Like, what's probability x less than equal to 1.5?
You stay at 1/6.
Correct. What happens at 2?
You jump to 1/3.
Let's say 2/6, right? Let's not be too
2/6.
fancy. Right, it's okay, 1/3 is correct. Right, and we see a pattern. What happens next? And so on, right? So let me redraw the picture. But you see there will be a jump here, a jump here, and then finally a jump here, right? Sorry, where was I? 1, 2, 3, 4, 5. There will be a jump, right? At 6. Sorry, my picture is back, but 6 here, right? And there will be a jump, right? Okay, let's see if we understand here. What's the value here? Corresponding to 6. That would be 1, right? So you see the CDF starts at 0, right? Or approaching 0, whatever, right? And rise to 1, right? But of course, it doesn't have to do so like continuously, right? So this is the mark of a discrete random variable. It jumps. But it jumps where? It jumps where the random variable have point mass. Okay. And how big is the jump? The jump will be the probability of the point mass. You understand? Right? And in between is constant because it has no density between this. It just has pure point mass. Now let's try a final detail. When a function has a jump, right, you have to do a dot and a circle, right? So for this, where is the dot and where's the circle? Is a dot above or below? Or is a circle here or a circle there? The circle is always below. Okay. Why? Because you see, probably x less than equal to 1 is 1/6. So if you touch 1, it jump up. But before that is the lower value. That's why, right? Probability x less than equal to a, x less than a is the left limit. Okay. So a CDF is right continuous with left limit. Right continuous. So there's a dot, right? Above. Everywhere. Okay. Like that. Okay. So step function is a hallmark of a discrete random variable in terms of CDF. Any question? All right, so let's stop here, right? And we'll continue on Wednesday.